Picture a building with a locked front door. Every night, the building manager locks it. Every morning, the tenants walk through it. Nobody thinks about it. The door is locked, the building is secure. Everyone goes home feeling safe. But the building also has a back door, and a loading bay, and 6 ground floor windows, and a ventilation shaft wide enough to crawl through. The front door was always locked. That part was true. But what the building manager was really doing wasn't securing the building. He was satisfying an assumption. The assumption that locking one entrance meant the building was protected. Cloud isolation works the same way. When engineers say their workloads are isolated, they're usually right about one specific thing. One door is locked, but around it, invisible and unexamined, are a dozen other assumptions about containers, about networks, about default configurations, about what internal really means. Those assumptions are locked doors that nobody checked. This video is about what's behind them. The first assumption: containers are isolated from each other. This one feels obvious. You run 2 containers, they have separate file systems, separate process trees, separate network interfaces. You can't reach from one into the other. The isolation is real, and you can verify it yourself. But here's what that isolation is actually built on. Both containers share the same Linux kernel, not a copy of the kernel, the same one. Every system call your container makes goes through the same kernel as every other container on that host. The namespaces and C groups that make them look separate are kernel features. They are enforced by code. They are subject to bugs. They depend on correct configuration. In 2019, a vulnerability called CVE 2019-5736 was disclosed in Runk, the container runtime used by Docker and Kubernetes. By running a malicious container image, an attacker could overwrite the Runk binary on the host. From there, they could execute arbitrary code as root on the host machine. Outside every container on it simultaneously, the containers were isolated from each other. The kernel was shared. The assumption was that the shared kernel had no exploitable path out. It did. One door was locked. The back wall had a hole in it. The second assumption: serverless means no neighbors. Serverless is the most isolated sounding thing in cloud computing. You don't manage servers. You don't think about virtual machines. You upload a function. It runs. It disappears. The entire premise feels like you're running in your own sealed bubble. You're not. Lambda functions run on physical hardware. That hardware is shared. AWS reuses execution environments. The same container your function ran in can be reused for the next invocation, possibly for a different customer. AWS is careful about how this works, and the security record is strong. But the assumption that serverless means physically isolated is yours, not theirs. AWS never said that. More concretely, AWS Lambda functions have access to an execution environment that persists between warm invocations. The metadata service didn't know the request came from an attacker. It saw an internal request from the instance. It handed over the credentials. Those credentials had permissions to read S3 buckets. All of them. The metadata service was internal. That was true. The assumption that internal meant inaccessible to an attacker with code execution on the same host was the engineer's own addition. AWS has since introduced IMDS version 2. It requires a session-oriented request that is harder to forge. The fix was there. The default was the old version. The assumption was that the default was secure. One door locked. Nobody checked whether an attacker inside the building could reach the key cabinet. The fourth assumption. My VPC keeps everything private. VPCs are real. Their isolation is meaningful. Traffic between your VPC and the outside world is genuinely controlled. But controlled means what you configured, and default configurations are not always what you imagine. An EC2 instance launched in a public subnet with a public IP address is reachable from the internet unless a security group explicitly blocks it. The default security group in some configurations allows unrestricted outbound traffic. An S3 bucket is not inside your VPC by default. Traffic to S3 from your instances travels over the public internet unless you configure a VPC endpoint. None of these are bugs. All of them are documented. Every single one of them has caused a real security incident, because an engineer assumed that in my VPC meant private by default in every direction. The VPC is a tool. It does what you configure it to do. The assumption that it wraps your entire environment in a private boundary automatically is yours. The VPC never made it. Look at all four of these assumptions and notice what they have in common. None of them were caused by the provider breaking a promise. None of them were caused by a 0-day in the hypervisor. None were caused by a flaw in the global network fabric. Every single one was an engineer confidently inferring something that was never actually guaranteed. Containers are isolated, true at the namespace level, assumed at the kernel level. Serverless means no shared state, true at the infrastructure level, assumed at the execution environment level. The metadata service is safe, true about its network exposure, assumed about server-side request forgery paths. VPCs are private, true about what you explicitly configure, assumed about everything else. The pattern is always the same. A real guarantee at one specific layer, an assumption at the layer just beneath it, and a breach exactly at the gap. This isn't an argument for paralysis. These tools are powerful, they are well designed, and they are worth using. But the engineers who stay safe aren't the ones who trust more. They are the ones who know precisely where their trust ends, and who go looking at the gap before an attacker does.